Next time you board a flight, on a beautiful, balmy 15-degree spring day, you might want to take a second to look out the window.
Yeah, just take a look at the wing.
Right. Appreciate the engineering happening right out there. Because that perfect, comfortable weather is, well, secretly one of the most dangerous times for a plane's engine to be running.
It really is.
Welcome to the deep dive. Today we are bypassing the surface level stuff. We're taking a fascinating journey straight through the anatomy of flight.
Straight into the mechanics of it all.
Exactly. Our mission today is to give you a shortcut to being perfectly well informed about the intricate mechanical symphony that makes air travel possible.
It's honestly a masterclass in physics and engineering, and it's just hidden in plain sight.
It really is. I mean, we're going to cover why a single tiny dead bug can completely blind a pilot to their speed.
Oh, that's a scary one.
Right. And why aircraft tires have these painted stripes on them just to see if the rubber is secretly creeping around the metal wheel.
Most of us just sit in our seats, put on our headphones, and completely ignore the sheer violence and precision happening mere feet away.
Okay, let's unpack this. Because before an aircraft can, manipulate the air to fly, it needs a self-reliant heartbeat.
It needs power.
Right. So we are starting with the piston engine. Now, a lot of people might look at a small aircraft engine and think it's just a big car engine with a propeller bolted to the front of it.
Which is a pretty common misconception.
Yeah, I mean, they both use internal combustion, they both have pistons, they both run on that four-stroke cycle, right?
Yeah.
Intake, compression, power, exhaust.
Right, the basic Otto cycle.
But I noticed a massive critical difference in the source materials regarding how they actually sustain that combustion, specifically how they get their spark.
That is a fundamental difference, yeah. And it really comes down to vulnerability.
How do you mean?
Well, think about your car. It relies on an electrical battery and an alternator to supply the current to the spark plugs.
Right, if my battery dies, I'm stuck.
Exactly. If the battery dies or the alternator fails, the electrical current is lost and the engine completely stops. You just pull over.
Which obviously you can't do in the sky.
No, an aircraft obviously cannot afford to just pull over.
Yeah.
So engineers completely decouple the engine's ignition from the aircraft's main electrical system.
Okay, so what do they use instead?
Instead, they use magnetos.
Right, the magneto. So a magneto is essentially a self-contained generator bolted right onto the engine.
Right, precisely. They use permanent magnets that are physically, mechanically rotated by the turning of the engine itself.
So the engine turns the magnet?
Yeah, as the engine gears turn, the magnets rotate, creating a magnetic field that induces a high-voltage electrical current. And that current is what fires the spark plugs.
So as long as the engine is rotating, it is generating its own lifeblood spark. It doesn't need an outside battery at all.
None at all. And to be safe, aircraft actually use a dual ignition system.
Two of everything.
Right. Two totally independent magnetos, each firing their own set of spark plugs in every single cylinder.
Which provides a backup if one fails. But the engineering notes point out that having two sparks firing simultaneously from opposite sides of the cylinder also ensures a balanced flame propagation.
Yes, it creates a smooth, even wave of fire pushing down on the piston, rather than an uneven burn.
But wait, I'm thinking about the physics of actually starting this thing. If the magneto needs the engine to be turning to generate a spark, how do you start the plane when the engine is completely dead?
That's the trick, isn't it?
Yeah, if the starter motor is only turning the engine over very slowly, wouldn't the magnetic rotation be too weak to make a spark?
It would be. Below about 500 RPM, that magnet just isn't spinning fast enough to generate a hot spark.
So how does it fire?
Well, there's a secondary, much more dangerous problem first, the timing of the spark. In normal flight, the spark fires slightly before the piston reaches the very top of its stroke.
So it starts the fire early to give it time to expand.
Exactly.
Yeah.
But if you fire that early while the engine is turning incredibly slowly during startup, the explosive gases will expand too quickly and force the piston violently backward.
Oh, wow.
Yeah, it's called a kickback, and it can physically shatter the engine components.
That sounds expensive. And dangerous.
Very. So engineers needed a way to delay the spark and make it super hot, even when the engine is barely turning. They solved this with a brilliant mechanical device called an impulse coupling.
Yes, I found this mechanism absolutely fascinating. To explain this to you, think of a wind-up toy car.
That's a great way to picture it.
You pull it backward slowly, winding up an internal spring to store energy. Then you let it go, and it violently snaps forward at high speed. The impulse coupling does exactly this for the magneto, right?
Exactly. During a slow engine start, a little metal catch temporarily locks the magneto's magnet in place.
So the engine is turning, but the magnet is stuck.
Right. As the engine slowly rotates, it's winding up a heavy coil spring attached to the magnet. What's fascinating here is the sheer elegance of that fail-safe design.
Because the engine keeps turning, winding that spring tighter and tighter until a release mechanism suddenly trips.
And boom, the spring unleashes all that stored energy, violently snapping the magnet forward at a super high speed, much faster than the engine is actually turning.
And that fast snap gives you the hot, high-voltage spark you need to start the engine. And because the mechanism held the magnet back while the spring wound up, it naturally delayed the spark.
Exactly. It delays the spark until the piston is safely past top dead center.
Top dead center being the absolute top of the stroke.
Right. That's the exact moment the piston reaches the top and is already on its way back down.
Right.
By delaying the spark until that moment, it entirely prevents that dangerous kickback.
It's a purely mechanical solution to an electrical problem. I love that.
It really is elegant.
So the impulse coupling solves the spark problem, but a spark means absolutely nothing without the perfect mixture of fuel and air. And this is where feeding the engine at high altitudes introduces some really bizarre physical phenomena.
Oh yeah, the environment up there changes everything.
First, the fuel itself. Aviation uses AVGAS, specifically a grade called 100L, which is dyed a very distinct blue.
The fuel chemistry is critical. That specific grade, 100 low lead, is strictly required to prevent something called detonation.
Detonation.
Yeah. In a normal engine, you want a smooth, controlled burn, that wave of fire we mentioned earlier. But under extreme pressures and temperatures inside an aircraft cylinder, a lower-grade fuel might spontaneously explode all at once.
Just from the pressure.
Just from the pressure before the spark plug even fires.
Like a diesel engine.
Similar concept, yeah. But in a gasoline engine, it's catastrophic. Detonation isn't a burn, it's a supersonic shockwave. It's an untimed explosion that hits the piston like a sledgehammer.
Oh, geez.
It will melt or physically shatter the aluminum pistons in a matter of minutes. The lead and the octane rating in 100 LL chemically slow down the combustion rate, ensuring it burns rather than detonates.
Okay, so we have the right fuel. Now, to mix that liquid fuel with air, many piston aircraft use a float-type carburetor.
Right.
And the core of a carburetor is something called a venturi. It's basically a pinched neck in the metal tube where the air enters.
Like an hourglass shape.
Exactly. As the air gets sucked into the engine, it hits this narrow pinched area and has to squeeze through. To get the same amount of air through a smaller space, the air physically has to speed up.
And when the air speeds up, its pressure drops.
And that low pressure zone literally sucks the liquid fuel out of a tiny nozzle, instantly vaporizing it into the passing air.
But that vaporization process introduces the invisible threat we teased at the very beginning, carburetor icing.
Right, the ice.
This happens in completely clean air, without any visible moisture like rain or clouds. When the liquid fuel turns into a vapor inside that venturi, it absorbs latent heat from its surroundings.
This is the part that genuinely defied common sense for me. Wait, so I can get lethal ice blocking the throat of my engine on a beautiful, balmy 15 degrees Celsius day?
You absolutely can if you understand the physics of phase changes.
It just sounds crazy.
The vaporization of the fuel, combined with the pressure drop of the air speeding up, creates a massive temperature drop inside the carburetor. The temperature in that metal throat can easily drop by 20 to 30 degrees Celsius in an instant.
So the best analogy I could think of is holding a spray deodorant can. When you press the button and the pressurized liquid turns into a gas, the metal can gets freezing cold in your hand.
That is the exact same latent heat drop.
Yeah, so the temperature drops so drastically that any invisible humidity in that comfortable 15-degree air suddenly condenses and instantly freezes to the metal walls of the carburetor throat.
And eventually it completely chokes off the airflow and the engine suffocates.
So how do you fight that?
Well, if we connect this to the bigger picture, this is exactly why pilots have a control in the cockpit called carburetor heat.
Carb heat, right.
Yeah, if they suspect invisible ice is forming, they pull this lever. It operates a mechanical flap that reroutes the ambient intake air through a metal shroud wrapped around the scorching hot engine exhaust pipe.
Oh.
It pumps that unfiltered, superheated air straight into the carburetor to melt the ice.
Though pulling that lever means you are pumping hot, less dense air into the engine, which actually costs you about 10 to 20% of your engine power while it's on.
It does. But, obviously, losing a little power is a necessary trade-off to keep the engine from choking to death.
Yeah, I'll take slightly less power over no power any day.
Exactly. So now the engine is running flawlessly, the magnetos are sparking, the fuel is mixed perfectly, the ice is melted. But internal combustion alone doesn't make an airplane fly.
Right, you have all this violent rotational energy, but you have to translate it into forward thrust.
Enter the propeller.
I think a lot of people just view the propeller as a giant fan, but it's not. A propeller is essentially a spinning, twisted wing.
Very much so.
Much like the main wings on the aircraft, a rotating propeller blade alters the airflow to create lower pressure ahead of the blade, which physically pulls the aircraft forward.
But the shape of that blade is incredibly specific and highly engineered. The key feature is the twist.
The twist.
The blade angle, or its pitch, is very steep right at the center hub, but as you move out along the blade, it flattens out, becoming almost completely flat at the very tip.
I was looking at the aerodynamic diagrams of this twist, and at first glance, it feels counterintuitive. Like, why would you want the tip of the blade to be flat while the center is steeply angled? Wouldn't you want a uniform shape to create uniform thrust?
It comes down to rotational velocity.
Okay, break that down.
As the propeller spins, the section of the blade near the center hub doesn't actually travel very far through the air to make one full circle. It's moving relatively slowly.
Right.
But the tip of the blade is tracing a massive circumference in the exact same amount of time. The tip is moving incredibly fast through the air compared to the root.
Here's where it gets really interesting. Think of a marching band turning a sharp corner on a parade route.
Oh, I like this.
Yeah, so the person on the inside of the curve is barely taking tiny steps, almost marching in place.
Right.
But the person on the outside edge has to sprint just to keep the line straight.
Right. They have to cover way more ground.
Exactly. If they both took the same size strides, the line would completely break apart.
That is a perfect way to visualize it. If the propeller blade had the exact same angle all the way down, the massive speed difference would cause the aerodynamic angle of attack to vary wildly.
So the fast part would act differently than the slow part.
Exactly. The fast-moving tip would take a huge, inefficient bite of air, creating massive drag, while the slow-moving root would do almost nothing. The blade is physically twisted to maintain a constant, uniform aerodynamic angle of attack across the entire span, balancing the thrust perfectly.
Now, a lot of smaller training planes have a fixed-pitch propeller, which is one solid, rigid piece of forged metal. The twist is permanent,
Yes.
but that's fundamentally an efficiency compromise because it's only truly optimized for one specific airspeed and one specific RPM. So advanced aircraft use constant speed propellers.
Right. In a constant speed system, the blades aren't bolted in place. They can physically rotate along their longitudinal axis in midair to change their pitch.
Wait, they move while they're spinning.
Yeah, it uses a highly complex mechanical governor and pressurized engine oil to constantly adjust the blades. If you point the nose down to dive and the engine tries to overspeed, the governor instantly pumps high-pressure oil into the propeller hub, twisting the blades to take a bigger, coarser bite of air.
So it bogs the engine down a bit.
Yes, it increases the air resistance, holding the engine RPM perfectly steady without the pilot doing a thing.
But hold on. If that system relies on engine oil pressure and mechanical rotation, what happens if the engine completely fails in flight? If the engine dies, the forward momentum of the plane is still forcing incoming air against the flat face of those blades.
Right, they're still out there catching wind.
So the propeller turns into a giant wind turbine, violently spinning the dead engine.
It's called windmilling, and you're right to point it out because it creates a massive, dangerous wall of aerodynamic drag. It basically acts like a huge air brake.
Which is the last thing you want when you're gliding without an engine.
Definitely not.
So the solution to windmilling is a mechanism called feathering. The pilot can command the propeller blades to mechanically rotate a full 90 degrees. Instead of the flat face hitting the wind, the thin leading edge of the blade slices cleanly straight into the oncoming air.
It immediately stops the rotation and eliminates that drag.
But even when everything is running perfectly, transferring all this power to the air creates some quirky aerodynamic side effects, doesn't it?
Oh, for sure. The spinning prop doesn't just push air straight back, it throws a high-velocity corkscrew of air backward. This is known as the spiraling slipstream.
A corkscrew of air.
Yeah, this tornado of air wraps around the fuselage and smacks directly into the left side of the vertical tail fin.
And that impact pushes the tail to the right, which forces the nose of the plane to violently yaw to the left.
Which is why, if you ever watch a pilot during a high-power, low-speed phase of flight like takeoff, they're constantly applying heavy right rudder pressure with their foot just to keep the aircraft tracking straight down the runway.
So the propeller is violently corkscrewing us through the sky. But to actually take off and land safely, we can't just rely on the static shape of the main wings. We need to fly very slowly near the ground. But slow speed means less lift.
Right, gravity starts winning.
So the wings need to dynamically change shape to grip the air. This brings us to high lift devices.
The fundamental aerodynamic goal here is to alter the wing's camber, which is its curvature and sometimes its overall surface area. This increases lift so the aircraft doesn't stall.
And a stall is when the wing stops flying and simply falls out of the sky.
Yes, exactly. It's a loss of lift.
The engineering breakdowns focus heavily on trailing edge flaps. And while things like plane flaps or split flaps just hinge down to change the shape, the Fowler flap is genuinely brilliant.
The Fowler flap is amazing.
It doesn't just hinge downward, it's mounted on mechanical tracks and physically slides backward out of the wing. It essentially builds a larger wing in midair, increasing the total surface area. It produces massive lift.
But there's another category used to combat stalls: slotted flaps and their leading edge equivalent, slats. When these deploy, they don't just change the shape of the wing, they open a highly precise gap, or slot, through the wing itself.
I had to read up on the aerodynamics of this because the mechanism is so clever. To understand it, you have to picture the boundary layer.
Okay, the boundary layer.
Think of the boundary layer as a microscopic blanket of air that actually sticks to the surface of the wing as it flies. At slow speeds and high angles, that blanket of air gets lazy. It wants to separate from the metal surface, become turbulent, and cause a stall.
So this physical slot opens up, capturing high-pressure air from underneath the wing, and forcefully shoots it up and over the top surface.
It's exactly like using a targeted leaf blower to blast high-energy air over the wing, gluing that lazy boundary layer back down onto the metal so the wing keeps generating lift.
It re-energizes the airflow. But it's important to understand how a pilot actually applies these physics. The first 10 or 15 degrees of flap extension give you a massive increase in lift with very little drag penalty.
Which is perfect for clawing your way into the air on takeoff.
Exactly. But when a pilot drops full flaps for landing, it's a completely different aerodynamic reality. Full flaps are purely about creating a massive wall of drag, allowing the aircraft to fly a steep, slow descent toward the runway without accelerating uncontrollably.
Manipulating the air with all these sliding flaps and slots requires knowing exactly what the air is doing around you. You need to know your speed with absolute precision. And the plane's sensory system for this is the pitot-static system.
It relies on a deceptively simple mechanical comparison of air pressures.
Just air pressure.
Yeah, you have flush-mounted static ports,
Yeah.
usually on the side of the fuselage, that measure ambient, still air pressure. Then you have a forward-facing pitot tube out on the wing that catches the POTUS.
Total pressure. Total pressure being the ram air violently impacting the open tube as the plane moves forward.
Right. The airspeed indicator mechanically compares the two. The difference between the violent ram air and the calm static air gives you dynamic pressure, which translates to your speed.
But the speed you read on the dial, indicated airspeed, isn't actually how fast you're moving through the physical space, right?
No, it's not.
Because air gets thinner and less dense as you climb in altitude, there are physically fewer air molecules hitting that pitot tube. So your true airspeed actually increases by about 2% for every 1,000 feet you climb, even if the mechanical needle on the dial hasn't moved an inch.
And that dial isn't just a speedometer. It's your primary structural warning system. The glass is painted with color-coded arcs.
Like a tachometer in a car.
Exactly. The white arc is the only safe speed range to deploy those fragile flaps. The green arc is your normal operating range. The yellow arc is a caution zone.
Caution meaning smooth air only.
Yes, you only fly those speeds in perfectly smooth air because a sudden turbulent gust could overstress the metal airframe. And finally, the red line, VNE or never exceed speed.
Because if you push the nose down and accelerate past that red line, you enter the realm of aeroelastic flutter.
Which is as bad as it sounds.
It's a resonant vibration, like a stop sign vibrating in heavy wind but happening to the entire wing structure. The metal flexes faster and faster until the wings literally fatigue and rip off the aircraft.
It's catastrophic.
But as vital as this instrument is, the mechanics of it introduce a terrifying vulnerability. So you're telling me a single dead bug hitting a metal tube can completely blind a pilot to their speed, or worse, confidently lie to them?
Unfortunately, yes. It all comes down to the mechanics of blockages.
Let's make sure we are picturing this mechanical deception correctly. Inside the airspeed indicator on the dashboard is a tiny, flexible metal diaphragm capsule.
Like a little accordion.
Right. Ram air from the pitot tube goes into the capsule, inflating it like a balloon. Ambient static air fills the case around it, resisting that inflation. Now, if a bug hits the front of the pitot tube and blocks it, but the little water drain hole at the bottom of the tube remains open, all that incoming ram air pressure leaks out the bottom.
Yes, it just bleeds out.
So the pressure inside the capsule drops. The needle drops to 0 knots, even if you're flying at 150 miles per hour.
The pilot loses their airspeed, which is bad, but it's obvious that it's broken. The truly dangerous scenario is a total pitot blockage, typically caused by flying into freezing moisture, where ice completely seals both the front entry and the drain hole.
Oh, no.
When that happens, the total pressure is permanently trapped inside the diaphragm capsule.
It becomes a completely sealed pressure vessel.
Exactly. The air has nowhere to go. Now, if the pilot pulls the nose up to climb, the ambient static pressure inside the instrument case drops because the outside air is getting thinner up high.
Right.
But the pressure trapped inside the capsule remains exactly the same. Because there is now less resistance from the case, the capsule expands, pushing the airspeed needle higher.
Oh, wow.
The airspeed indicator has entirely stopped measuring forward speed and has effectively turned into a broken altimeter. It will tell the pilot they are accelerating as they climb and slowing down as they descend, entirely divorced from reality.
That is genuinely terrifying. Your instruments are giving you highly confident, perfectly reverse information.
It has caused some very serious accidents.
I can imagine. Now, assuming the pilot navigates the sky perfectly, avoids the ice, and manages their flaps, the final challenge of flight is transitioning back to the Earth. Meeting the ground requires systems that can handle massive kinetic impacts and brutal thermal friction. Landing gear.
You'll generally see two configurations in light aircraft. The traditional tailwheel with two main wheels up front and a small wheel on the back, or the tricycle gear with the single wheel up front under the nose.
Tricycle is more common now, right?
Oh yeah. The tricycle gear provides vastly superior forward visibility on the ground and prevents the aircraft from flipping over its own nose during heavy braking.
But the real magic is in how they absorb the shock of a multi-ton aircraft dropping out of the sky. They don't just use bouncy metal springs, they use fluid dynamics. They use oleo-struts.
Those are incredible pieces of engineering.
It's a telescopic metal cylinder filled with incompressible hydraulic fluid on the bottom and highly pressurized nitrogen gas on top. When the plane slams onto the runway, it forces that hydraulic fluid through a tiny hole, an orifice, past a tapering metering pin.
Which is really hard to do quickly.
Exactly. This violently restricts the fluid, absorbing the immediate kinetic impact of the touchdown. Then the fluid compresses the nitrogen gas, which smoothly cushions the rest of the airframe's weight as it settles.
But the nose wheel on a tricycle gear has its own unique, highly destructive vulnerability during touchdown and high-speed taxiing. Shimmy.
Like a wobbly tire.
Yeah, it's a rapid, violent side-to-side oscillation of the front wheel, much like a broken shopping cart wheel, that can literally tear the front of the aircraft apart. To stop this, engineers install a hydraulic shimmy damper.
And how does that work?
It acts exactly like the oleo-strut's fluid restriction, but horizontally. Slow, deliberate steering inputs easily push fluid through the damper's orifice. But a rapid, violent shimmy tries to force the fluid too fast, dynamically locking the piston and instantly dampening the vibration.
And then there are the tires themselves. Aircraft wheels aren't like car rims, they are two split metal halves bolted together. Because the rotational forces of a landing aircraft hitting the concrete at 150 miles per hour are so incredibly violent, they suffer from something called tire creep.
Tire creep, yeah.
The rubber tire casing can physically slip and rotate around the metal wheel rim over time.
Which is highly dangerous for tube-type tires, because the inflation valve is attached to the inner tube, but it protrudes outward through a hole in the metal rim. If the tire and tube rotate, but the metal rim stays locked by the brakes, that metal edge shears the valve completely off.
Just snaps it right off.
Instant explosive flat tire.
It's exactly like wearing loose socks on a slippery hardwood floor. You go running, your foot stops, but the sock keeps rotating around your ankle until it tears.
Exactly.
To monitor this, mechanics paint aligned creep marks, just simple painted stripes, across the tire sidewall and the metal rim. During a pre-flight walk-around, if those painted stripes are misaligned, they know the rubber is secretly creeping and a blowout is imminent.
This raises an important question regarding thermal management as we bring the aircraft to a halt. We've talked about absorbing kinetic impacts with fluid, But what about the brakes?
That's a lot of heat.
You have an object weighing thousands of pounds, moving at over 100 miles per hour, and you have to stop it on a short runway. The brakes convert all of that kinetic flying energy directly into sheer heat through friction.
Just burning it off.
Light planes might use a single hydraulic disc brake, but heavy commercial jets require multi-disc stacks of alternating stators and rotors just to absorb and dissipate that massive thermal load without catching fire or melting the rubber seals.
So what does this all mean for you? Well, the next time you're a passenger on a flight, don't just stare at the clouds or bury your head in a movie. Look out the window at those Fowler flaps sliding backwards on their mechanical tracks to stretch the wing into the wind.
Listen to the pitch of the engine change.
Yeah, as the constant speed propeller dynamically twists its blades in midair to bite the air perfectly. Think about the oleo struts waiting to force hydraulic fluid past a metering pin the exact second you touch the runway. Realize that you are not just a passenger. You are riding inside a masterclass of physics and fluid dynamics.
And I'll leave you with this final thought to mull over. Everything we just explored, the self-reliant independence of the magnetos, the phase changes in the carburetor, the pressurized engine oil twisting the propeller, the pneumatic pressures of the landing struts, it all relies on the physical, tangible properties of combustion, pulleys, and fluids.
The physical mechanics.
Exactly. But as the aviation industry looks aggressively toward the future of fully electric aircraft, we're going to eliminate magnetos, engine oil, and complex fuel manifolds completely. When we strip away these mechanical marvels of the 20th century, what entirely new, unseen physical vulnerabilities will take their place in the skies of tomorrow?